PID controller: proportional, integral, differential. Complicated. Let's keep it simple. If our controller only works with proportional of the error, then it will oscillate. I'm too low, I go upwards. I'm too high, I go downwards, and so on. It may converge after a while, but it's going to be very inefficient and very tedious, those movements. We want to have it as efficient and converge as fast as possible and in a smooth way, meaning I'm in the right height. For that, we need some sort of prediction of the future. So a proportional going to be our present. It's also the same letter, so it's fine. We want to be able to predict our future height and somehow take it into consideration with respect not just for our proportional, but also what's going to be my height in the next sampling rate, in the next click of the time, in the next sample of the time, right? And integral going to be our past, but let's, for simplicity, keep the integral away for a few minutes, and let's define a PD control algorithm, which is performing the following. The same thing with the proportional. I have my current error, and I react with respect to that. But I'm not only reacting with respect to my current error or current difference between my desired and my reading of the sensors. I also react with respect to my future approximation. In order to be able to take in consideration my future height, I'm going to compute my z velocity, my rate of changing with respect to height. For simplicity, you can think of it as the change, the difference between the current error and the last error. If the error shrinks, then I'm in the right rate. If the error increases, I need to put more power. So, in a way, the D predicts my future, or look at the rate of change. And if the rate of change is in the right way, then it might be able to predict that I'm going to be in my right. So assuming this is the 1 meter above the table here, I'm here, but I was there in the last time. So I'm here, I'm in this movement. It predicts that next I'm going to be there, then I might want to be start decreasing the throttle because I'm going to be there. So if I decrease it too much, the next step, I know the rate is not going upwards, so I need to increase it a little bit more. But in a way, if the P and the D are balanced, then instead of doing that, I'm going to do this. So the D predicts my future position using the rate of change. And by that, in a way, it shrinks the oscillation. In a way, it restricts the overshoot of the P by refining it, by looking at the next steps. All those are linear controllers, meaning I have a fixed parameter which says how much gain should I give to the current proportional to the P. I have another linear parameter, fixed parameter, which in a way give me the D weight or the gain. I combine them together, just sum them together, and give the throttle a PD controller.